Right, we are back at Holden again for a morning walk about time. Still on this time thing. This is maybe part 3 of a series where we've been going into time a little bit from a physics perspective, but also from an observe time for yourself perspective. And I think both are very useful. But I did have more to say because, you know, time is a thing that we can measure, right? Well, we say we can measure it, but in some sense we're not really measuring time. And this is kind of what I wanted to get to, is time in some sense is a fiction. And what's more real are these states that we're talking about. And you know, you can think of time as being an ordered set of states, right? Especially in the quantum world, we look at time, or we say there's quantum states and there's transitions between quantum states, and that everything occurs not continuously, but as a series of transitions from one quantum state to the next. And all these transitions have probabilities, and that the world works in that way, right? It transitions from one state to the next. And this kind of goes back, so I did just a little research on the atomic clocks. Still didn't spend a tremendous amount of time on it, but it turns out that, and I guess I sort of knew this, but I just forgot a lot of the details, that what, like an atomic clock like cesium, that's based on cesium, and by the way, there are many others in development that even go beyond the classic cesium atomic clock, which just shows how long I've been out of it. I remember that being the basis for atomic clocks back when I had, you know, when I was in physics studying it in school over 20 years ago. And really have not kept up on it since then, you know, other than a cursory knowledge of what's happening. But it's interesting to see what's going on, and there's even imprecision in these atomic clocks. And there was a graph, the Wikipedia page for atomic clocks is a good place if you're interested in even just starting. There's a little graph on there that shows the accuracy, how the accuracy of atomic clocks has improved over time, because they keep coming up with different ways of isolating the atoms from the environment. That it's a necessary requirement to have the atoms as isolated as possible, which means, you know, even though temperature is not a big factor, it's one of the things that makes atomic clocks more accurate, is they are not sensitive to temperature because they are based on transitions between atomic states. Quantum, it's sort of, you can think of it as it's a quantum effect, in that a cesium atom has like a base state and an excited state, and the difference in energy between those two states is related to the frequency of radiation that gets released by these atoms when they drop from their higher excited state to the lower state. Right? There's a quantum of energy, which is essentially a photon with a certain energy, and that because it has an energy, it has a certain frequency, and that frequency is what is essentially time. That's how we measure the time, the oscillation, that measurement of the frequency, and how many of these transitions occur in a regular way, right? It's very similar to the pendulum swinging back and forth, is the state going between the excited state, the ground state, releasing this energy, a very particular energy of excitation, right? Which is what excites it. You need the energy of that frequency to excite it and then to cause the transition. So when they get a resonance going in this, normally it's a microwave cavity of some kind, and there is this oscillation, it's like a resonance that's built up, and they can measure the resonance and the transition of these atoms, and they can count the number of times that the atoms go from the excited state to the ground state. And it's a very complicated process, which is also what makes you think of, so this is time? Like, what's interesting is we think of time as this ethereal thing that is somehow separate from space, like things are occurring in space. Like let's just take the cesium atom, that it's going between its excited states, its ground state, and all this is occurring. We think over time, time being like a line we draw on a graph, you know, that indicates there's some time that exists separate from the states that are occurring. But all we're doing is measuring the transitions of these states. They're occurring in a sequence. You know, you're going from the ground state to excited state to ground state to excited state. And counting the number of times these state transitions occur and using that as a measure of time. But there's nothing other than just the observation of these state transitions, right? All we're really observing are some number of, we're counting, right? We're counting the number of clicks, the number of, it's like a pendulum, you count the number of times it swings back and forth, and that's an indication of time. And in some sense, we're counting these states, which also requires memory, by the way, because if you had no memory, you couldn't keep track of counting. So without memory, there's no time either, because there'd be no way to say how many states had you'd only know the current state you are in, never the previous state, never the other state. You're in the now can be regarded as the current quantum state, right, if you want to think of it that way. And the only way we know there's different quantum states is because there's some recording of something about the previous quantum states, right, which is what we might call memory. So only because we have memory do we have a concept of time. There would be no concept of time if we didn't keep track of past states in some way. You know, so there has to be an accumulation, even for time to exist. It's not just like to count something, right? You need a memory. Even in a computer, you have to keep incrementing a number, which means you have to remember the past number and increment it by 1 to even count. So even counting, the most basic element that we have, requires memory. So time, without memory, there would be no time, because there'd be no counting. So let's just, you know, there's the implication of that. So then you have all these clocks being designed. Let's just say these are the most precise clocks in the world, but we talked about everything is a clock, in a sense. Anything that transitions from one state to another state, which is everything in the universe, could be regarded as a clock. We just have particular devices that we try to isolate from the environment. And that's what's interesting, right? We isolate it as much as possible. And then there's a regularity to the state transitions that we observe by isolating it as much as possible from the environment. But you can never isolate it from the environment, right? If you completely isolated the clock from the environment, you'd never be able to read any information off that clock. You know, it's like you have to interact with it to even observe it. So even the interacting of it changes the fact that it's not isolated, you know? So a clock is never totally isolated. And this is why the accuracy may improve over time, but the accuracy is never perfect, because there is no perfect time. See, we're striving for some ideal idea of time as being this thing that exists outside of space, right? And that the clocks are measuring this ephemeral thing called time, when in fact all we're doing is observing state transitions and counting them. And it's fundamental to get down to what time really is. It's just a counting process of some system that we observe, and we try to create this standard, right? The whole NIST, National Institute of Standards and Technologies, right, is behind a lot of this. And some of their latest clocks are based on optical methods, and what was it called, optical fountain? I haven't even investigated all this because it's interesting, but at the same time, just it's making the point that I'm trying to make, which is that it's like as technology improves, this measurement of time, measurement in quotes, will continue to improve, but we're not really improving measurement of time. We're simply finding another device that we can say is that we can count more of, right? So like they're moving towards optical clocks because there's a higher frequency and you can count more, right? And so by being able to count more things in an interval, you can get more precise measurements of time by the way we're defining it, right? As we're defining time in terms of these states and transitions. And this is what, where I'm getting at is time is not a separate independent thing. It's very much related to how you choose to measure it. And you can devise much more complicated systems for measuring time, but it's almost like we need to stop saying measuring time. You're simply developing a system for counting states and then using that as a reference to other states that are not part of the clock, right? Because a clock wouldn't be terribly useful if it was in isolation, total isolation. The clock is useful when you interact with it. So you look at the clock next to your bed to figure out what time it is. If that clock were totally isolated from the environment, in a box, hermetically sealed, whatever, it's not useful because you can't interact with, you can't see the time. To read the time, you can't have it isolated from you. There has to be an interaction between you and the clock to even perceive the state changes that are occurring. So a clock is only useful in measuring something other than the clock. And this is where it gets tricky, because you can think of the system of the clock, and let's just take you as an example, right? You and the clock. Or, let's take an apple, rotting apple, right? That you could take a time-lapse photography of, and you could watch that apple change over time, right? And go through all these chemical changes, and go from a nice apple to a pile of mush. And we say that takes a certain amount of time, and what's really happening are all these chemical processes, which are all could be regarded as just changes of state at a massive level, if we want to consider the system as like a quantum system with state changes occurring all the time at some rate, right? But how do we know the rate? It's simply an ordered sequence of states, right? State 1, state 2, state 3, and then you could regard, an apple going from its really nice state to its final mushy state as being some number of state transitions, quantum state transitions. It's many more than this, but let's say it's 1,000,000. It's 1,000,000 state transitions, starting from the initial state to the final state, to get from a nice looking apple to a mushy apple. And that ordered set of states has no time, in that there's no time associated with an ordered set of states. It's simply 1, 2, 3, 4, 5. It's an index. So if you look at time as an index in that sense, it's just a sequence of states that are occurring in a certain way, and you're transitioning from one state to the next state based off some set of rules. We could say those are the laws of physics, or whatever the rules of the system are that govern the motion of the transition from one state to the next state, which in math is called a Markov process. You just go one state at a time, essentially, and say the current state only depends on the past state. And then there's, probabilities of transitioning from one state to the next state, which can be called a Markov process. But we don't even need to talk about that, but it's just because when you talk about discrete states, things like that come into play. There's mathematics for state transitions. So if you look at things as everything in the universe is unfolding as a sequence of states, then a clock is just a sequence of states that's unfolding. But there's a relationship, because a clock is not an isolated system, there's some relationship between however many state transitions occur on the clock and then the number of state transitions in the rotting apple. So let's say the clock is measuring, the clock is undergoing very rapid state transitions. So in the same, let's say, period of time, right? But we have to be careful, because let's say after every 100 clicks of the atomic clock, the apple goes through one click of its state, from 1 to 2 or 2 to 3. And then another 100 clicks occur on the atomic clock, and then another one state change occurs in the apple. And this relationship between the number of state transitions of the clock and the number of state transitions of some object near the clock is the usefulness of the clock. Because we say we can measure the clicks in the clock and relate that to the age of the apple. Only if there's a relationship, though. If there was no relationship between the number of clicks on the clock and the number of clicks it takes for an apple, then there would be, in some sense, total disconnect between time, between what we call time and what's happening with the apple. And how does the apple even have any sense of time? It simply is always in its current state. This is where observation comes in, because you only know what state you're in by looking at the clock. So like the apple itself, let's just say the apple has, well, this is where I was going to use us as awareness. Let's say the apple has some awareness. It has no idea, it's only ever in its current state, and can only ever be in its current state, and has really no knowledge of the past state or the future state, unless the current state records something from those states. There's memory, right? But let's say the apple has no brain, has no memory, no way to record information about past states, which is really what all the brain does, records information about states, which itself is just in the present moment, in the current state. So it's never in the past state. It's always an evolving current state that retains some information from the past state. And there never really is anything other than just a currently evolving state. There's just now, right? That now is the current state. And we say it's changing only because we have memory of the previous state, right? I'm sorry I repeat, but I'm just emphasizing, like, these, as these ideas come across. Because why this is important is how we choose to measure time with a clock and then relate it to other things is where the problem comes in, because a clock really is only measuring itself, its current state, but we interact with that clock and count the number of states that it goes through. But we're relying on there being a consistency or a correlation between the number of states that the clock undergoes and the number of states that this other system that isn't the clock undergoes. And this is how we measure time, right? So we measure time right now. I mean, I'm walking through the field, and time, we'd like to say time is evolving, right? But what's really happening is just there's change that's occurring. And I remember that change only because I have memory. I would not remember it if I had no memory. I would only know what's now, what's the current state. And I don't even know that I would know it, because there's no knowing in the traditional sense without memory. So there would just be the present state. No knowing of the present state, just the present state. And maybe there's an awareness, right? Something that's other than knowing of the current state. But if you're only ever aware of the current state, then how do you even differentiate between one state and the next? They could all be the same state, right? And this is why I keep going into this, because we only know about different states because we have memory of past states. We have clocks because we want to count states, and we measure time in this way. A clock is only useful if there's a correlation between things, and that's only because they form, the clock and the non-clock form a system that are correlated or related. The states of one system are related to the states of the other. And so that there's some relationship, like that's what I was saying before, 100 state changes of the clock maybe corresponds to one state change of the apple, or any other system. Pick your favorite system, right? Or you could even say 2 atomic clocks can measure time between themselves. So let's use the cesium clock as one system, and then we have another clock which is, say, based on optical methods, which can measure, which has more clicks, right? It's a higher frequency, and there's more state transitions of the optical clock in the period of time, so to speak, of the cesium clock, because it has a lower frequency. So you could say maybe 100 state changes of the optical clock correspond to only one state change in the cesium clock. So there you have 2 different metrics of time, and you're comparing states to states. And only because there's a relationship, right? If that relationship were off, changed, then there would be no meaning to the clock. The clock counting its states would have no meaning if there wasn't a larger system of which that clock is part of. So this is often, like, even in relativity, you'll see the examples in any relativity book that show a person on the ground with a clock next to them, a person in a spaceship with a clock next to them. Because the clock next to you implies a relationship, that it's in your frame of reference, right? That somehow you're not moving, you're whatever's, you assume by proximity that clock just being near you is somehow its state transitions are correlated to your state transitions. But the clock that may be on a spaceship going near the speed of light is related to you, but in a different way. There's a different relationship between the clock right in front of you and the clock on the traveling ship. And it's this different relationship that causes the different rates of time to occur, different state transitions, right, between what's happening in some other system. And we can define this as separation, right? Separation is sort of that, there's a clock that's near you that I can touch and hold and feel, so I feel like it's part of my system. I'm interacting with it. I'm related to that clock in a different way than I'm not related to a clock that's in my neighbor's house even. It's further away, and what time it's saying. I would have to run over there and see it, and then I'm near it. Or I'd have to put a camera there and observe that clock through electricity passing through wires to where I'm at. So see, a clock becomes less useful the further away from you it gets, because I interact with that clock less. So the relationship between you and the clock is very essential for time to have any meaning. Time is measured by that clock. And this is kind of like where all of this goes, right? You see where we're headed, where becomes a discussion of state transitions and ordered state transitions rather than the flow of time as some ethereal thing that occurs. And we say that time moves forward because you can say there's a sequence to the states, right? That time doesn't generally reverse itself because the states don't go in the opposite order. There is some ordered states. And in that sense, the ordering of the states gives direction of time. Simply because, like, certain, if you're in one state, the next state is more likely because you're in that state. But then once you go to the next state, the previous state is not as likely as some other future state, right? So it's the probability of these states occurring that defines the motion of time, not time causing these states to move. It's simply saying the probability of transitioning from one state to the next depends on the current state. So in that current state, like, say there's 3 states, past, present, and future, state 1, 2, 3. And you go from state 1 to 2, so 1's the past, 2 is the next state, which we could regard as now, and then 3 is, say, the future state. And there's many possibilities. Well, in the past, I was going to say, when things actually occur, it's not probability. It's one state or the other state. We don't know what the future state's going to be based on our current understanding, right? We can't predict that future state, but we know the probability of each future state occurring. That's what quantum mechanics gives us, essentially. And if we're in a certain state, those probabilities depend on the state we're in, not on the past state, generally. And that's where Markov comes in. It just depends on where you are now, not the past state plus the present state. And so the past doesn't matter in that sense. It's just the now, and then a probability of transitioning to another state. So if you're in state 2, you would say the probability is higher that you're going to transition to state 3 rather than go back in time and transition to state 1. Right? And this relationship is, let's just bring in probability, but I mean, we don't have to, that's an abstract concept maybe just as much as time is. But we can say the way we understand the mechanics of space and time right now is through this probabilistic state transition logic. And this process, right, this occurs, you can define states at the macroscopic level, not just the quantum level. I mean, people that do dynamical systems, that are studying systems that change over time, define states. It could be a biological system, right? And the states could represent observable things about that system. And then you're watching that system evolve over time in a certain way, right? It doesn't have to be it doesn't have to be a quantum system, I guess is the point there. It can just be a labeling of states of however you choose to observe any system, right, at any scale. And so these concepts apply not only at the quantum level. It's very clear at the quantum level because we've gotten down to something that we can observe these discrete state transitions, like the states of a cesium atom, right? We can see the energy, you know, and going from a ground state to an excited state, and then releasing photons as you go in the reverse direction is a very well-known quantum mechanical event with very quantized energy, right? Packets of energy that we can measure that are very much the same every time. Not exactly, and that comes to the accuracy of these clocks. There is some imprecision even to measuring that, and a lot of it's because of the interaction with the environment, which you can never totally remove. So I know this is going everywhere. We're all over the place here, and this is because this is free thinking. We're starting with something and we're going into it, and we're looking at this in this way. Though we're sort of taking call it physics, but it doesn't have to be physics, right? It's just we're observing how the world works, how we interact with the world, how we define time, how we define clocks, how we use clocks. When is a clock useful? When is a clock not useful? You know, and don't take any of this for granted, you know, and break this down into your own observation of things. How do you observe time, right? How do you know that time is passing? How do you sense the passage of time? And does time, when you feel time, you know, sometimes you say the day, today seemed like such a slow day, right? Well, why did, you know, I know for me, I can feel the passage of time differently to where hours can go by and I feel like no time at all has passed, right? So I didn't have a sense of time passing. Then there's other times where, depending on what's happening, I feel like an infinity of time is passing in a fraction of a second because there's so much that I'm thinking about, or, you know, the thought processes are occurring more rapidly, right? And again, this is just like the frequency of the atoms in the clock, that if thoughts occur more rapidly, there's like more state transitions, right? And with more state transitions, we perceive a greater passing of time. So if thought is occurring at different rates, we would perceive time differently, psychologically, because that's how we perceive time, through our thoughts and memory. So very much so, time depends on thought, our perception of time, and on memory, right? And all these things. And, you know, and this gets to where this is not just physics, because you don't want to take this observed perspective where we are somehow separate from the things that we are measuring. You know, we are part of the system. We are part of the entire system. The human being, as an observer, is part of the system that's being observed, including clocks. So there's a relationship, and I just want to bring this back in, that if there were no relationship between things, there'd be total chaos. Clocks wouldn't matter. Clocks could run, you know, sometimes you'll see movies that show clocks moving like really fast, right, or really slow. And imagine the chaos that would ensue if clocks did that. If they just ran at different rates at different times, we would have no sense of time. We would almost call that insanity, right? That the fact that things are correlated and ordered is sanity. There's a saneness to things, right? That if things were totally out of whack, no correlation between the clock's passage of time, the clock state transitions, and my state transitions, then I may perceive time, a day can feel like a month. I may look at that clock and have just totally different perceptions of the passing of time. And that does happen. We all know that happens. So it's just, but most of the time there's an orderly passage of time. You know, we have this sense of time passing. A lot of times I can tell how much time has passed just by how much thought has passed, right? Like if I'm in a certain mental state, I know, okay, based on how many thoughts I've had, right? It's like the number of thoughts I've had is some measure of the passage of time. Which is also why when you have fewer thoughts, fewer state transitions in the brain, look at it that way. A thought is like a state transition in the brain. Fewer of those, you have a perception that less time has passed, right? And people who enter deep meditative states, in some sense, right, are playing around with, I think, those state transitions in the mind, to where the mind, still a machine, still a device, a state machine, can be put in different modes of thinking, where more or less thoughts occur, and maybe of different types, and all those are different. But this is what's interesting, right? You don't break out of the mind or the brain itself by simply putting your brain into a different state. So just causing your brain to say slow down or have less state transitions isn't fundamentally changing the nature of the brain. It's still the brain. It's still doing what a brain does, just in a different mode of operation. This is one of the reasons why all of these techniques of meditation aren't really doing anything other than putting your brain into a different state, a different operational mode. So what? It's like comparing one atomic clock to another atomic clock. It's still essentially the same thing, just moving in a different direction. What you want to do is see the brain, that entire system of the brain, in all of its states, in every possible state, the meditative state, the normal waking state, the sleeping state, right? All these different states of the brain, have an awareness of that entire process, not just be in one state or choose one other. Choose the peaceful state of meditation, the sleepy self-hypnotic state, over the awake state. So awareness of your mind and the consciousness and what's happening in your mind is our perception of time. And that can occur while you're awake, while you're asleep, while you're in so-called traditional meditative states, the jhanas, deep meditative states. I mean, take your pick, what you want to call all this. So the true awareness is beyond all that. It's not one state of the brain observing another state of the brain. It's like an awareness of all states of the brain, awareness of how everything works, the nature and structure of thought, that all this is occurring, and these state transitions of the brain are the same as the state transitions of nature, and not at a conceptual level. Everything we're talking about here is conceptual, but at an awareness level. Observe the mind as it undergoes state transitions, and what it's doing, and how it remembers the past, and how we perceive time, and what would time be without memory, and how time is a counting process, right? So if we count differently or at a different rate, time can pass at a different rate. It's not remarkable. So relativistic time is not an insane idea. It's the most ordinary idea, that counting is time, counting state transitions, and those state transitions locally can occur at a different rate comparatively to what might occur somewhere else, right? And that's like general relativity will tell you that a clock in an intense gravitational field will tend to be slower than the clock outside of that intense gravitational field, which essentially means if you have two clocks together, they're both clicking at the same rate. You take one, put it on a spaceship, go near a black hole where the gravitation is very strong there. Let that clock stay in that vicinity for a while, and then bring that clock back. You'll see less ticks on the clock that experienced the intense gravity, because we understand this relationship between the states. But there's nothing strange about it. It's just gravity, being near another massive object, changes state transitions. It slows down those state transitions. And why is that so strange? Because there's an interaction there. That clock is interacting with a massively large body, which means it's in a different environment than I am in. Why wouldn't its state transitions change? Like, it's not isolated. Because see, we think of the clock as an isolated system. It's not an isolated system. It depends on the system of where it's around. It's what's near that object, right? It's a temperature. It's like the environment, you can't remove it completely from an environment. Even an atomic clock, right, in an intense gravitational field, is in a different environment than a clock that is not in that intense gravitational field. So you may be able to say an atomic clock is insensitive to temperature, but it's not insensitive to gravity, right? We know that, but that's okay. Gravity is another environment. It's another force, another field. It's another thing we can measure. So what you're really just saying is a clock, you can never be isolated from its environment, and depending on its environment, undergoes different state transitions. One of the factors of that environmental difference is temperature, that sometimes can affect normal clocks. But then even an atomic clock, which depends on state transitions in atoms, also can be affected by gravity, which is another environmental factor, or acceleration, getting into a spaceship. So without knowing the exact, you don't even have to know the math behind any of this, right? Just that there are different environments, and that once you see time then as just these local state changes, there's nothing remarkable about time passing at different rates in different environments, because it's not time that's doing anything. It's the probability of these state transitions is changing. And since time can be thought of as the indexing of these ordered states, there's nothing magical about time. Time is just an indexing, no more. So it loses its universal significance, that there is this ethereal thing called time that we're measuring. We're not measuring time. We're measuring the number of state transitions, counting. That's different. And that counting can occur at different rates for the clock, depending on where the clock is. This is why I still wanted to say more about time, because we have concepts of things like time, right? And based on those concepts, we live a certain way. We see the passage of time and we think that it's universal, or even our own age, or, is time we measure by a clock. And we have our own internal biological clocks. We have the clocks of day, the sun rising and falling. We have the clocks of the seasons. And, of course, we record things in our memory. So we have the idea of the passage of thousands of years of time, right? Which we would have no idea if all the history books were gone. Everyone's memory was gone. We'd have no idea what the history of this planet ever was. All we'd know is where we are right now. Why isn't that all we know? Why do we? It's because of all that baggage we carry around with us of the past that changes our perception of time now. So when you think about it that way, right? Because a lot of this is about, our inner exploration as well as the outer world. And how we perceive time is very much a part of how we live our life. We feel old, or some people don't feel old, and why? Because the clock says, the calendar age says, because we've measured the number of ticks in a clock and we've assumed there's a correlation between that and us that may not be there. So you can just lose this whole importance of time as a measure of even yourself when you understand time as simply this counting process, this ordering process, which is, it's funny because this just removes a lot of, like, I remember when I was initially confused about relativistic time, because I had in my mind this idea that there is a universal time that exists, and then only because of that was it confusing. Without that concept, there's nothing confusing about it whatsoever. It's what you observe in the world, which just goes to show that we need to observe this world in such a way that we don't let our biases and our past and our knowledge distort what we see. Whether it's time, space, whatever it is, see with clear eyes, which is see the now, see the current quantum state. Don't let the past quantum state interfere with the current quantum state, of which there only is. There's only one current state. And this is also like, there's almost an epiphany here, right? Which is just that there's only now. There's only now, which you could regard as the current quantum state. And we only have knowledge of past states because of memory. We only think there's future states because of memory, because we have an idea about a future state from a current state. But in fact, there is only the current now. Just let that sink in. And stop measuring things. Stop measuring everything and comparing everything to everything else. And it's a different awareness of things, right? And you don't need to be a scientist. There's no science necessary. There's nothing. Just observe time, right? So it's about time that you observe time for yourself and stop listening to what experts are telling you. So I feel like I've said enough about time. So I guess 3 episodes of this, whatever you want to call it, feels like I've said enough about time. I've said enough. That doesn't mean that you need to stop your own inquiry into time. Like, this is this brain's processing of its awareness of time, leading to this string of words that have no truth in them. Right? These words have no truth. Don't believe anything I say. I mean, there's no reason to believe a word, but see it for yourself. That's truth. See it for yourself, and then there's no need for words. No need for anyone's explanation to tell you what's what, or what time is. You don't need anyone to tell you what time is. It's what you experience. It's your thoughts. You perceive time all the time. Your thoughts are time. See that thoughts and time are the same. That your thoughts are a measure, a metric of time in your own psychological perspective. Your brain is like a state machine that is undergoing state transitions, and that is your only perception of time. Can you be aware of that? Aware of your mind as just transitioning from one state to the next, aware of the state transitions, right? And aware that that memory is part of that time perception. So, all right, I think that's enough. Let's get back to living in this world of space and time.